Right. So, welcome everyone to another American Physical Society Climate Physics seminar that is run by the Topical Group on Physics of Climate. This is Kianush, one of the seminar's committee members, and today I'm very happy to host Jörn Callies from Caltech. So just a couple of words before we just get going. The seminar is run using the Zoom webinar format, so that is also new to me. So during the talk, you can submit your questions in the Q&A section, or also, I guess, in the chat as well, and we will address them after the presentation. Also, we try to unmute you after the presentation. Just use the raise your hand feature in the Zoom, and then I can unmute you, and then you would be able to ask questions. We definitely encourage questions, especially from students and postdocs. So without any further ado, it's a pleasure to introduce Jörn Callies from Caltech, where he is a professor of oceanography and environmental science in the Division of Geological and Planetary Sciences. Jörn holds a diploma degree from the University of Hamburg, Germany, and a PhD from MIT Hui Joint Program in Oceanography. He works to better understand the ocean's circulation and how it regulates the Earth's climate. By probing the ocean with in situ acoustic and satellite observation, developing simplified dynamical models, and deploying detailed numerical simulation, he aims to extract the laws that govern this turbulent fluid. So today, Jörn is going to talk to us about using earthquakes to measure deep ocean warming. And Jörn, the floor is yours. Thanks.
All right, thanks very much. Thanks very much for the invitation to speak here. This should be fun. Yeah, so I'm going to talk to you about this work that we've been doing over the past couple of years, trying to use earthquakes to measure the warming of the deep ocean in our warming climate system. And what I'm going to try to do over the next 45 minutes or so is convince you that that's less crazy than it sounds, and we can actually make some progress here. So before I jump in, I want to acknowledge my wonderful collaborators on this project. This has really been an interdisciplinary effort in collaboration with seismologists. And I also want to highlight in particular Sheree Peng here, who's led the work that most of it that I'm presenting here today. Okay, so to start motivating why we might want to improve our sampling of the deep ocean and our estimates and observations of the warming of the deep ocean, I want to start by giving a little bit of an introduction about the role that the ocean plays in the climate system, and in particular how the transport of heat from the surface to the deep ocean really is an important control on the rate at which our climate system is warming. So just very basically, the ocean really has a large heat capacity that dominates our Earth's energy budget. And so if we take account of the energy that we've trapped on the planet by primarily increasing greenhouse gas concentrations in the atmosphere, almost all of that energy has ended up in the ocean and has ended up warming the ocean. More than 90% of the energy that's shown here over time. The three blue bars here are the ocean partitioned into the top 700 meters, 700 to 2,000 meters, and deeper than 2,000 meters. Some of the energy has gone into warming and melting ice. Some of it has gone into warming the land, the solid earth. And then it's only really this energetically, this tiny sliver that has warmed the atmosphere, right? The global warming signal that we're all experiencing. Okay, so from an energy perspective, the ocean really is front and center in our transient climate system. To make that point a little bit more concrete and really highlight the transport of heat from the surface to the deep ocean, I want to consider this very simple conceptual model of the climate system. So on sort of decadal timescales, we can think of the response of our climate system to the forcing that we're imparting on it, again, primarily increasing the concentrations of greenhouse gases in the atmosphere, can be understood by thinking about the response to the radiative forcing F acting on the surface ocean. So my climate system consists of just the ocean. You can see that I'm an oceanographer, right? And so we want to consider the response of that surface ocean to that forcing F, right? There's a feedback. A warmer climate radiates more efficiently to space. Right, this is principally the Planck feedback, sigma t to the fourth, but there are other important feedbacks, water vapor, lapse rate, cloud feedbacks, and so on. That all gets summarized in this feedback term here that I'm assuming to be proportional to the temperature response of the surface ocean. Okay. And then in addition, there is a transfer of energy, a transport of heat from the surface to the deep ocean, right? And because the deep ocean is warming much more slowly than the surface ocean, that heat transfer we can think of as, again, to leading order very roughly, as proportional to the warming that the surface ocean has experienced, right? If there's more warming in the surface ocean, then the same circulation will generate a larger heat transfer to the deep ocean. Okay, and so on a decadal timescale, we can think of the response to the forcing then in terms of the temperature evolution of that surface ocean. C is the heat capacity, right, as the sum of these three terms, forcing tending to increase it, and then the two transports out due to feedback, radiation to space, and transfer of heat to the deep ocean. Now, on the decadal timescale, these terms mostly balance so that this tendency term is relatively small. And so we can solve this equation for the response, right? We can solve for T prime, and that is simply the ratio of the forcing and these two parameters, the feedback parameter and the heat transfer efficiency that I'll call gamma. Okay. And so, the field pays a lot of attention, understandably, to this feedback parameter lambda that measures how much does the climate warm for a given amount of forcing once it's reached a new equilibrium, right? The inverse of lambda is the equilibrium climate sensitivity. But in the transient, as we're ramping up the forcing and our climate system is catching up to that forcing, right? The heat transfer to the deep ocean and the heat transfer efficiency plays a similarly important role. Okay. Now this heat transport, right, is not nearly as simple as sketched here in this diagram, right? It depends on processes that are completely understood from a physical perspective, and that are typically parameterized in climate models. These are mesoscale eddies that we'll talk more about later. They're the ocean's weather, the equivalent of the high and low pressure systems that we have in the atmosphere. Overflows, internal wave breaking, boundary layer turbulence, you name it. Lots of small scale processes all contribute to that heat transfer from the surface to the deep ocean, either directly or through shaping the large scale circulation that is affecting that heat transfer. Okay. And so I would argue that observations of the deep ocean warming are then crucial for our understanding of these processes and for the evaluation and calibration of climate models. Okay, and so how do we observe the warming of the ocean? Over the past 2 decades or so, the principal source of data has come from these Argo floats. These are autonomous floats that are deployed very sophisticatedly, like in the picture. These have a bladder on the bottom that allows them to change their buoyancy, and so they can go up and down in the water column autonomously. They are typically parked at 1,000 meters depth, drift around for 10 days, and then they deflate their bladder to go down to 2,000 meters depth, turn on their instruments. So on the top here, there's an instrument that measures the temperature, the conductivity, and the pressure, and then inflates the bladder and rises through the water column all the way to the surface. Once it's reached the surface, it links back via satellite the data that it has collected on that way up, that profile of temperature, salinity, and pressure. Okay. There are 4,000 of these floats across the world ocean, represented by the black dots here, giving an amazing data set of the temperature of the ocean, of the top 2,000 meters of the ocean, every 10 days. This is a big international collaboration, and this array of floats has been at this sort of global coverage since about 2005. Okay, and so when you put that together, these are then the estimates of changes in the ocean temperature over the past 20 years or so. So this is starting in 2005, and I'm plotting the temperature anomaly here as a function of time. This is adapted from a nice paper by Hakuba et al. Last year. Okay. And so this is I should say, the globally average temperature anomaly. And so this includes the warming of the surface ocean as well as the deep ocean. So this is the volume averaged temperature anomaly. And the different lines here show different estimates from different groups around the world who take this data as well as other data and come up with a global estimate of the average warming. Right, I'm highlighting 4 of them here, and you can see that there's quite a bit of disagreement between these different estimates, right? And the principal difference is how they decide to map out the data, fill in gaps, and interpolate in space and in time. The numbers here that I'm quoting, these are the equivalent energy imbalances at the top of the atmosphere. Because the ocean dominates the energy budget of the planet, this is actually our best estimate of the imbalance that we're currently experiencing. So measuring the deep ocean or the whole ocean warming is our best estimate of the energy imbalance, given here in watts per square meter at the top of the atmosphere, averaged over the global surface. Right? And so you can see that depending on your choices of how you map out this data, you get an answer that differs by a factor of 2 or so. Okay. And so while there's important work to be done to understand better and improve these mapping techniques, as well as quantify their uncertainties, right, my feeling is that if your answer changes by a factor of 2, depending on what you do, you really have weak data constraints. You're under constrained by the data, and more data would help. Now, why is that if we have 4,000 of these Argo floats roaming the ocean, how can we still have that large an uncertainty in our estimate of ocean warming? Well, one aspect of that is that the temperature anomaly that we're trying to constrain here is relatively small, right? Over a 20-year period, it's something like 0.025 Kelvin, right? 25 millikelvin. That's a small number. I'll emphasize that this is, again, averaged over the whole volume of the ocean. The surface ocean has warmed much faster than the deep ocean, but in a volume average, in particular in the deep ocean, the warming rates are quite weak, right? So we're looking for signals that are on the order of 10 millikelvins per decade. Now that's challenging to measure in an ocean that looks like this. Okay, this is from a numerical simulation that we've run in my group. This is showing you a map from a snapshot of that simulation of the surface kinetic energy, right? The kinetic energy of the currents at the surface ocean. This is in the Atlantic. This is the Gulf Stream that separates from the east coast of the US at Cape Hatteras, and then juts out into the interior of the ocean, meandering as it goes along and shedding these eddies here that are about 100 kilometers in scale. So these are our mesoscale eddies that dominate the kinetic energy of the broad ocean globally. And these are associated with temperature anomalies in the surface ocean of multiple Kelvin. And so they're orders of magnitude larger than the climate signal that we're trying to detect. Right? You can see that there's lots of complexity to the circulation of the ocean. There are these mesoscale eddies, smaller scale, submesoscale eddies, fronts that undergo frontal instabilities. There's internal waves and so on. And so, right, we really have to understand the sampling problem as a sampling problem of a turbulent ocean, of a very dynamic ocean. And so if you now imagine that, with 4,000 floats, you're trying to sample this turbulent ocean, right? You're still undersampling it, right? That can be seen explicitly in this map here. This is a global map of the sea surface height anomaly. Okay, so this is from satellite altimeters that are mapped out globally. This is on a particular day in November in 2019. And that gives us a reasonable estimate of where we have eddies and how strong they are. right? This is not a measurement of the interior temperature, though it is correlated with it. Um, Okay, and so you can see that, in particular in the western boundary current regions, like here with the Gulf Stream, we have strong mesoscale eddies. They're again about 100 kilometers in size. And if you look across the world ocean, really these eddies are much smaller than the spacing between Argo floats, right? If you take the area of the ocean and divide it by 4,000, you get about 300 by 300 kilometers in area that is sampled by one float. And so we're really undersampling this mesoscale eddy field globally. Okay, we can see that more explicitly when we zoom in. This is a zoom in into the western North Pacific. Okay, so we have the boundary current there as well, just like the Gulf Stream, the Kuroshio that runs along the boundary here and then separates from Japan into the interior of the North Pacific. And as it does so, again, it meanders and generates mesoscale eddies, as seen here again in that sea surface height anomaly from satellite altimetry. Right. Again, I'm superimposing the location of the Argo floats on a particular day. And again, you see that even though this is an area that is understood to be undersampled and the Argo program deploys preferentially in this region, it still undersamples the mesoscale eddy field, right? You see that this eddy cyclone here is not sampled at all. Some of these anomalies are sampled, but by and large, there's a lot of them that are missed. And you can see that in temperature anomaly estimates as in one of these mapped products, right? This is the temperature anomaly. This is a weighted average of the deep ocean temperature. You can see that it has positive anomalies where these three meanders are, but it misses a lot of the mesoscale anomalies. Again, I think one should work to improve these mapping techniques, and here's our version of that, where we think we can do slightly better. But what remains really is that the sampling is just not dense enough to map out mesoscale eddies, and that contributes substantially to the uncertainty once you globally integrate to the Earth's energy imbalance. Okay. And so we ask, can we do better, right? And can we really substantially add to this database, right? We don't want to have an alternative to Argo, but we want to contribute to that estimate of the global energy imbalance, as well as regional estimates of the warming that can tell us a lot about the dynamics of the ocean and its response to the climate forcing. So can we substantially add to the database? One way that we think we can do better is by taking the ocean's temperature acoustically. Okay, so this is an idea that goes back to Walter Munk and Carl Wunsch, who proposed it back in the 1970s. And the idea is to transmit sound across ocean basins. And that is enabled by the ocean's waveguide. So the ocean has a minimum in sound speed at mid-depth. And this is because of the sound speed's temperature and pressure dependence. The surface ocean is warmer than the deep ocean, and so the sound speed increases towards the surface. At the same time, the pressure increases with depth, and so the sound speed increases as we go into the abyss. And so as a result, there's a minimum in sound speed at mid-depth that acts as an acoustic waveguide. And this allows us, the so-called SOFAR channel, allows us to transmit sound from a sound source thousands of kilometers and really globally to some receiving hydrophone suspended in the water column. Okay. Now, if you transmit that sound, you can measure very accurately the travel time of that sound between the source and the receiver. And because the sound speed in seawater depends primarily on temperature, right? If you can measure changes in that travel time, that relates to the path integral of the temperature anomaly along the path of that sound wave. Okay? And so you can invert that and say, okay, I can measure the integrated and really integrated over thousands of kilometers temperature anomaly by measuring changes in the travel time. Right? This has key advantages because your measurement itself averages over mesoscale eddies, right? If you can make this measurement over thousands of kilometers, there's many mesoscale eddies in between, and so you're intrinsically averaging those anomalies. Just to give you a sense for the numbers, if you're looking for a climate signal of some 20 millikelvin, right, sort of nominal signal we expect over a decade, right? If we have that anomaly over a 3,000 kilometer long path, then that changes the travel time by 0.1 seconds. Okay, it's a very small fractional change, but we have accurate clocks, and that's easy to measure. Okay, so that worked, and there was a serious effort. Maybe I'll go back here. There was a serious effort in the 90s to build up a global observing system based on this idea. This is the ATOC experiment in the Northeast Pacific with two sound sources, one off Monterey and one off Kauai, and then hydrophone stations that were repurposed from the SOSUS array that the Navy had that it used during the Cold War for anti-submarine warfare. And so, this idea worked, and you might ask, why aren't we pursuing it? Well, the problem was that this ATOC experiment really ran into a public outcry that led to concerns that the sound sources that were used, right, to transmit the sound long distances, were going to interfere with the communication and ultimately harm marine mammals, in particular whales. Whether this is actually the case is still debated, but nevertheless, the public outcry led to the program being mired in controversy, and never really came to fruition on a global scale. And so what we're going to do now is try to resurrect this idea, but use sound sources that are natural, right? Instead of using artificial sources deployed in the water column, we're going to use earthquakes. Earthquakes make sound, right? They generate strong sound waves in the ocean when they erupt underwater. And these are some of the loudest noises that we have in the ocean, save for nuclear explosions. And so the idea then is to go back here, right, and say, okay, if we have an earthquake somewhere deep down at depth that ruptures, right, this earthquake makes seismic waves that propagate through the solid earth, right? And these seismic waves, they generate shaking on land that is picked up by a land station, right? But they also shake the sea floor, and that shaking generates sound waves in the ocean. So these seismic waves propagating through the solid earth get partially converted into sound waves that then propagate again long distances through the ocean, again enabled by that mid-depth waveguide, the minimum of sound speed at mid-depth. Okay, and they can be then measured by hydrophones, again suspended in the water column. Okay, so here's an example of how this works. Okay, so this is again our region here off Japan. Right, this is Japan. The Kurashiro comes along here and separates into the interior. And we're going to consider an earthquake that occurred off the coast here, right? And that earthquake generated a sound wave that propagated across the ocean here to a hydrophone station that is at Wake Island. This is a small island atoll, and there's been a long-running hydrophone station there maintained by the Comprehensive Testbed Treaty Organization by the United Nations. They maintain a global network of such hydrophone stations for the nuclear monitoring, for the monitoring of nuclear tests. You can imagine that if you detonate a nuclear bomb underwater, that also makes very loud sounds that also propagate long distances. And so this is one of the ways to monitor the Testbed Treaty. Okay, we're going to use that hydrophone station to listen for these sound waves generated by earthquakes. Now, what's different about our approach here, right, using natural sources compared to an artificial one, is that we don't have control over the sources, right? And in particular, we don't know exactly where and when the sound wave gets generated, right? Where and when that seismic wave gets converted into a sound wave, or even where and when exactly the earthquake ruptures. Okay. You can do the usual triangulation with multiple land stations to constrain where the hypocenter of the earthquake is, but that's not nearly accurate enough to get useful measurements of ocean temperature change. Right? Again, we need temperature changes, need to constrain temperature changes that are quite small, and therefore travel time changes on the order of a tenth of a second or less. Okay, so what we do instead, and this is really the key trick that makes this work, is to use not single earthquakes, but repeating earthquakes. Okay, these are earthquakes that happen at different times, but more or less on the same patch of the fault. Okay, so you have your a patch of the fault that is sticky, and that ruptures, right, as the faults as the plates move relative to one another. And it can rupture in the same patch multiple times. It can be days apart, weeks apart, months apart, years apart, or even decades apart. Okay? And what's cool is that if that rupture occurs in the same location, because the propagation of the seismic waves through the complicated crust so sensitively depends on the location of the earthquake, right? The scattering history on the way of these waves to the land station is completely different even if you move the earthquake by one wavelength. We can tell on the land station whether two earthquakes are repeaters, whether two earthquakes happened in the same spot. Okay. So here on the right, I'm showing an example of where we've identified two earthquakes as repeaters, and then we're making a temperature measurement with that. Okay, so these are two earthquakes. The first one occurred on March 15th, 2011, and the second one on the 1st of January in 2014. Okay, these are the traces on the land station over here. So this is the wave that has propagated through the solid Earth, right? A P wave and an S wave here. And you can see that these waveforms don't line up. And they don't line up because the catalog that we've used to reference the time here has a location and time error. Okay, there's an origin time error, but when we line up these two waves, right, when we maximize their cross correlation, they line up almost perfectly. Okay, and so these waveforms really are very similar, and we infer from that that these earthquakes have occurred in the same location. Okay, and what's more is when we line up these waveforms, we can correct for that origin time error and really posit that these earthquakes happened in the same spot, and we can line up their origins by lining up the waves that have propagated through the solid Earth. Okay, and then on the bottom here are the waves received on the hydrophone. Okay, so now the seismic waves have generated sound waves in the ocean that then have propagated some 3,000 kilometers to Wake Island, right? And again, these waveforms look similar, but they don't line up, right? And so we can play the same game. We can maximize their cross correlation, line them up optimally, right? And from that, we can see that in 2014, the wave arrived 0.45 seconds later. Okay, so even though these waves were generated in the same location, right, it took 0.45 seconds longer for the wave to propagate from the earthquake to this hydrophone in 2014 than it did in 2011. Okay, so the inference then is that the ocean must have warmed in the meantime and the intervening 3-some years, and we can use this measurement of the travel time change to constrain that temperature change. Okay, so here's how we do that quantitatively. We use a sensitivity kernel that's shown here. This is the basically how much travel time change you get per degree of temperature change at a given depth. Okay, there's a strong depth dependence of the sensitivity. It peaks somewhere around the the axis of our waveguide, where the sound speed is minimal, right? If you change the temperature there, you change the travel time of these waves the most. If you change the temperature of the surface, that doesn't affect the travel time at all. If you change the temperature in the deepest parts of the abyss, it doesn't change the travel time at all either. Okay, so what we're really measuring is this weighted temperature change, where the weighting is supplied by the sensitivity kernel to give us that travel time change between repeating earthquakes. Okay, we can turn that around and define an actual weighted temperature change with, again, K here, the sensitivity kernel is defining that weighting. Right, in the usual way, this is a weighted temperature change. But then this numerator here is just our travel time change, and the denominator here we get from the sensitivity kernel. And so this is our measurement, right? We can measure the travel time change, and we know the sensitivity kernel. I should say that we calculate these from numerical wave propagation through the mean state of the ocean, and then the adjoint of that. And so we can get the sensitivity constrained by numerical simulations. Okay, so if we apply that now to our example of repeating earthquakes between 2011 and 2014, right, where we observed a travel time change of 0.45 seconds, right, we divide by this bulk sensitivity of 6 seconds per Kelvin, and we infer that between these two dates, on average, right, with the weighting defining that average along that path, the ocean has warmed by some 75 millikelvin. Okay, so that's the basic measurement that we're making. Now, we can make these measurements for small earthquakes. This is crucial because if you can make these measurements for small earthquakes, you get many of them, right? There's many, many magnitude 4 earthquakes. And so we can make measurements here off this change in the travel time, in this case, from some 1,500 earthquake pairs. Okay, so these are, again, just the pairs that we've identified as repeating events, where we can line up the waveforms and measure the change, the change in the travel time on the path to the hydrophone. Okay, and then we want to turn that into something more interpretable than the actual travel time changes between two particular dates. And so we estimate time series of this temperature anomaly, again, averaged along this path and with a weighted average in the vertical as defined by the sensitivity kernel, using a Bayesian inversion. We use a linear Gaussian inversion here, assuming that we know something about the prior statistics of the temperature anomalies in this region. And in fact, we use in situ observations, principally Argo observations, to inform those priors. Okay, so then when you put everything together, this is what you get. Okay, so this is now the path integrated, path averaged temperature anomaly, again, between Japan and Wake Island, with a vertical weighting defined by the sensitivity of this wave propagating through the ocean, and converted right into this temperature anomaly. You can see that we have temperature anomalies on the order of 0.1 Kelvin or so. Okay. And the uncertainty here is giving you a 2 sigma uncertainty of our estimate as inferred by our inversion. Okay, so think of this time series as being generated from some 1,500 pairs of earthquakes that all give us measurements of some delta t, right? Some difference in temperature, and we sort of string them together optimally to generate this time series. First off, you see that the uncertainty drops quite substantially in 2011, and this is because that's when the Tohoku earthquake occurred, the megathrust event that caused a devastating tsunami. And whenever you have a megathrust event, right, there's an aftershock sequence of lots and lots of small earthquakes, and many of those small earthquakes are repeating earthquakes that allow us to make this measurement. Okay, so the reduced uncertainty in the aftermath of that megathrust event really is um, a signature of that aftershock sequence that decays relatively slowly over time. Okay, now if you look at this time series, you see that there's lots and lots of anomalies, right? So you see anomalies on the order of 0.1 seconds, right, that have a time scale of a few months or so. And and so even though we're averaging over the whole path between Japan and Wake Island, right, mesoscale eddies still dominate this variability, right? And so even though we're not aliasing these eddies like in situ observations do, right, even in that integrated measurement, they still dominate the anomalies. And this is, largely because we're in a region where these mesoscale eddies are particularly strong, right? A lot of this is the meandering of the Kuroshio current that generates very large temperature anomalies. There's a 10 Kelvin or so temperature drop across the current. And so there's a very large temperature anomaly associated with the meandering of that current. Um, Right. You also see that there's sort of a decadal scale trend here. And you might notice that that trend is much larger than what I told you earlier we should expect. Right. This is on the order of zero point 0.1 Kelvin. Right. So this is something like an order of magnitude larger than the average trend that we expect. Okay. Now this is what the same estimate looks like if we just base it on in situ observations. So this is mostly Argo observations, but we also use any shipboard observations where you take a research vessel and you lower a probe into the ocean and take its temperature. So all of that data is in here as well. You can see that there's some consistency. You have some anomalies here in the completely independent conventional data that we see in the seismic data as well. You see a similar trend over the decades, but you have a much larger uncertainty, right? And this is again due to that undersampling of the mesoscale eddy field in the conventional data, even with 4,000 Argo floats. Okay, nevertheless, there's some information there, of course, and so we can combine these two data sources into a combined estimate of this time series, and that reduces the uncertainty further, particularly in the time frame before the megathrust event, before 2011, where the seismic data is a weaker constraint. Okay. Now, we want to go further back in time, and one way we can do that is by using, instead of hydrophones, which have not as long a record, use seismic stations on land. So this is Wake Island. This is the island off which the hydrophone station is located, and there's a seismic station on the beach somewhere around here. Right, and that seismic station has been operating for decades, and in particular, it has had a digital data record since the 1990s. Okay, now this seismic station also picks up on these waves, on these sound waves that propagate through the ocean. Right, these waves propagate as sound waves, but then once they hit the island, right, they hit the seafloor, get again partially converted into seismic waves that then propagate to the island station and generate ground motion that the seismometer picks up. Okay, and so with this data, we can play the same game, look for repeating earthquakes over now the time frame going back much further, in this case to 1997, I believe, and then use all of the pairs of measurements between repeating earthquakes to generate this time series of temperature anomaly, again averaged along that path. Okay, you can again see that after 2011, we have a much better constraint because we have lots more earthquakes, but there are some constraints all the way back. I should also mention that using the seismic station is less ideal than a hydrophone because these records tend to be noisier And so you can't use as small an earthquake to get a good signal, get a good measurement. And so there's fewer earthquakes that you can use, and therefore fewer constraints. Okay, then if you again compare that to the conventional estimate, right, again from Argo data as well as shipboard data, we can see that that data also becomes a weaker constraint as we go farther back in time. No surprise, the Argo array really came into being in the early 2000s and really reached its current coverage sometime in the mid to late 2000s. And so you can see that the uncertainty is much weaker, much smaller here than it is before that. Before that, you're very much constrained to shipboard measurements, which are very sparse, few and far between. Okay. Um, and so again, you can put the two together to get a combined estimate. And while the constraints are relatively weak before the mid 2000s, there are some constraints, and they do help us learn about the history of the deep ocean in this region. And in particular, this seems to show that the trend that we saw between the mid 2000s and present right, really seems to be more of a decadal scale signal. Seems to be sort of a flat, if not a cooling trend before that. And this is not inconsistent with our understanding of the system, that there's decadal scale variability in the location of the current and how much it meanders. And that will all be reflected in the temperature signal in the deep ocean because water masses get rearranged and you have warmer or colder water along the path. Okay, so I want to zoom out a little bit and show you the potential of these kinds of measurements on a global scale. So everything I showed you today was from this location here, right, using earthquakes off Japan received on Wake Island. We have a few other examples where we've made these measurements. First measurements actually were from the Indian Ocean. We used earthquakes off Sumatra, received on Diego Garcia here in the central Indian Ocean. There's another island station as well as a hydrophone station here. And so we sampled the deep equatorial Indian Ocean over here. We used the same earthquake to sample this path here to Cape Leuven off the coast of Western Australia. And so that is the longest path so far that we've sampled. And we've seen lots of anomalies from eddies that are shed by the Leuven current coming along here that propagate westward across this path. It's really cool. Okay, and then we're in the process of making measurements in the Southwest Indian Ocean using earthquakes along the Fiji-Tonga Trench, received on an island station here on one of the Polynesian islands. And what's cool here is that we're making these measurements not only of using the wave that propagates in the ocean waveguide, but also a wave that propagates on the interface between the solid Earth and the ocean. And that interface wave is much more sensitive to the abyss than it is to the mid depths. And so from that, you can get much more information about the vertical structure of the temperature change that has occurred in this region. But really, the reason I show this map is for you to imagine that you have all of these earthquakes here along the Pacific Rim, and all of these will generate sound waves that propagate long distances through the ocean, and that can give you information about the ocean. And what's more is that data has been collected for decades, and so you can go to the record and look for these signatures of these waves coming from around the Pacific Ocean, say on Wake Island or some of the few other stations that are across the Pacific Ocean, to really try to constrain better the global or at least basin scale warming of the ocean. The measurements are a little bit more challenging in the Atlantic. In the Atlantic, most of the seismicity is along the mid-ocean ridge, the mid-Atlantic ridge running along the middle of the basin. These are earthquakes that happen in the rift valleys or along the axis of the trench, and that ridge doesn't quite reach far enough into the ocean's waveguide to efficiently excite these waves that propagate long distances. And so you tend to need larger earthquakes to make these sound waves. And so again, that translates into fewer constraints. We think one can still make these measurements, but one shouldn't expect as good a constraint as from the Pacific Ocean. One other example I'll mention is a couple of months ago, there was a mega thrust event off Kamchatka. There will be a strong aftershock sequence that will generate similarly strong constraints as we've seen for Japan. And also, there was a similar mega thrust event in the 1950s. And so there might be a potential for using data from almost a century ago to try to constrain a much longer scale temperature change. Okay, so let me wrap up, summarize. We're using seismically generated sound waves to obtain constraints of the warming of the deep ocean. And these constraints quite substantially reduce the uncertainties in the large-scale estimates, principally because these acoustic measurements average along the range, right? They average in space intrinsically by integrating by themselves. And so they don't alias mesoscale eddies, but they average them out. And so that really helps constrain the large-scale changes in the ocean. We have an existing record, right? This is data that was collected for other reasons for decades. And so we can constrain past change. We can go back in time, including going to the pre-Argo era where the constraint from conventional data is quite weak. Right? And then finally, I mentioned the waves that sample the abyss. They're called the Scholti waves. These are the interface waves between the solid earth and the ocean. We can also gain some information about the vertical structure of temperature change from making these measurements at different frequencies. And so if you make the measurement at a few different frequencies, the sensitivity kernel changes, shifts in the water column. And so you can use that differences in the measurements between these different frequencies to constrain the vertical structure. That's what I have. Maybe I'll put up my references, and I'm more than happy to answer any questions.
Thank you so much, Jörn. That was a really nice presentation. So we have a couple of questions already in the Q&A. So if you don't mind, you can start answering those, and then we can get any questions that we can unmute anyone that has. Just raise your hand, please. I can see and unmute you.
Okay. Okay, first question, do you expect the deep ocean temperature to have smaller timescale variations, seasonal, transient days? Right. So we're measuring whatever's there, right? And so yeah, these deep ocean temperatures their variability is dominated by mesoscale eddies. Mesoscale eddies are primarily generated in the thermocline in the top 1,000 meters or so of the ocean, but they extend into the deep ocean, and they extend into where the measurements that we're making are sensitive. And so yes, we expect mesoscale anomalies to be dominant. And so the game is to generate long enough and time series, as well as map out these temperature changes as much as we can, to find the climate system and climate signal in that noise, if you will. Okay, I wonder how much global estimate of the ocean warming could benefit from the earthquake data. More local path averaged. Yeah. Right. So the spatial distribution is an interesting one. So maybe let me go back to my map over here. Right. So the way that these acoustic measurements were originally phrased is with the term of tomography, right? And so what really was envisioned was that you had lots of sources and lots of receivers with lots of crisscrossing paths, so that you could use the information from all of these paths to, in the end, invert for the spatial structure. right? And you can imagine to do the same here, right? If you have a sufficient number of stations, you have lots and lots of sources. And so you get lots of crisscrossing paths to try to infer the spatial structure. Um, it would be great if we had more control over the sources, right? You would not put your sources all along the Pacific Rim, say. You would put some in the interior of the Pacific as well. But this is what we have to work with. And so, I think of this as, providing some constraints on the large scale structure, um, but really as a complement to all of the other data that we're collecting with the Argo program. Right? And so once you put them together, you also have a much better constraint on the spatial structure. What about density changes? Right, salinity also affects density. Um, so what really matters is the change in the sound speed, and the impact of salinity variations on the sound speed is much weaker relatively to temperature anomalies than its impact on density anomalies. And so these acoustic measurements are really quite strongly dominated by temperature anomalies. What's actually more important than salinity is currents. If you have a current along the path, right, they Doppler shift the sound waves, and that generates a larger signal. Again, it's an order of magnitude or more down from the temperature signal, but it's more important than salinity. Any idea of what's going on with the uncertainty in the temperature anomaly from the seismic station in 2020? Let me go back there. Yeah, I'd have to look. I would suspect that there's a data gap either in the hydrophone or in the land stations that we use as reference. We have a few land stations for reference, but I don't think there was a gap in earthquakes. I think it's a data gap. Just kernel change in time, slightly, right? These anomalies are quite weak. Um, right, the ocean hasn't changed its temperature very much, and so the linearization that we're doing and just calculating the sensitivity kernel based on the mean state is quite a good one. But in principle, you could take that into account and use an evolving state to look for changes in the sensitivity. I would think that that has no impact on the uncertainty. Right, do ocean currents shift travel times? Yes. This is um, mostly a signal that we think we saw. We weren't quite sure. We think we saw the signal in the equatorial Indian Ocean. There also was a megathrust event there, and so in the immediate aftermath, we have basically hourly resolution of the travel time change along that path. And there seems to be a tidal signal there, a 12-hour signal that we think was due to the Doppler shift by the tidal currents. It's quite small relative to the temperature signal, but because we had the high resolution, we think we saw it. Because we only have that one example, we weren't sure enough to write that up. But yes, currents affect the estimate. For mesoscale eddies, the temperature effect dominates over the velocity effect. Again, there's a lot of averaging, but yeah, the Doppler shift is part of the signal as well. Again, ocean salinity, third order effect, I would say. People argue that storms can create stormquakes. Can generate 3.5 earthquake magnitude earthquakes. That would be cool. I have to look into that. If you see it on a seismic station, right, the question then becomes how strongly do they excite sound waves in the ocean? And so again, you need to couple with the waveguide at mid-depth. And I would suspect that if you have a surface forcing, that couples relatively weakly. But maybe there's an indirect coupling through the solid earth that helps. compare temperature change from any recent earthquake against any Argo or CTD measurements. So we always need two earthquakes, right? I try to make that clear to get a measurement of temperature change. A single earthquake doesn't help us. And so recent earthquakes only helps insofar as if they're paired with an earthquake earlier on. And so, yes, the record becomes better as we increase in time and becomes quadratically so, right? It becomes better quadratically because, you find constraints on the past with earthquakes that occur now. But yeah, one single earthquake that doesn't immediately generate a constraint. Can you use your improved estimate on the variability in ocean heat content on a few paths to address the question of how reliable global estimates of mean trends in ocean heat uptake are? That would be an interesting exercise, right? Basically, compare our estimates to all of the estimates that I showed in one of the early graphs and see how they fare. Um, uh, yeah, certainly that would be a good sort of calibration of their mapping techniques, definitely.
Yeah, perfect. Thank you, Leah. We covered all the questions in the chat or the Q&A. So probably we have time for a couple of more questions, two more maybe. If there's any question from the audience, just please raise your hand and you can just talk. Okay, I do not see any other questions.
Thanks for all the ones that you put in the chat.
Yeah, that was really cool questions actually. I really like the questions. All right, so then I would like to thank Jörn one more time. Thank you so much for your time. It was a really great presentation, very interesting topic. And with that, I would probably stop the recording as well.
All right, thanks so much for having me.
Uh, Perfect.